Assalamu alaikum and welcome students to this program on electrostatics. In this program we will discuss a few basic concepts of electrostatics. We will discuss Coulomb's law, electric field and its intensity, electric flux, Gauss's law and its applications, and then we will go on to a very practical use of electrostatics in the capacitors, and then we will talk about electric polarization. Now let's start our program, let's start our discussion with Coulomb's law. This is a law which tells us that whenever we have two charged bodies, then there would be a force between the two charges, and this force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Let's look at it mathematically. Now here I have 2 point charges, and the magnitude of them are q1 and q2. The distance between the two charges is r. Now the force between them is called an electrostatic force, and if I represent this by Fe, then according to Coulomb's law, Fe is directly proportional to the product q1 q2 and inversely proportional to r square. Introducing the constant of proportionality, Fe is equal to k q1 q2 over r square. This k is expressed in terms of another constant epsilon naught, and k is equal to 1 over 4 pi epsilon naught. Epsilon naught is called the permittivity of free space, and it has a value of 8.85 into 10 raised to power minus 12 Coulomb square per Newton meter square. Now Coulomb's law is most commonly expressed in this form, which says Fe is equal to 1 over 4 pi epsilon naught q1 q2 over r square. Now this force is a force of attraction if the two charges are unlike, which means if I have a negative charge and I have a positive charge, then the force between them would be a force of attraction. But if I have two like charges, which means that q1 and q2 are both positive, or if q1 and q2 are both negative, then the force between them would be a force of repulsion. We have just learnt that according to Coulomb's law, the electrostatic force between two charges is inversely proportional to the square of the distance between them. This means that as we move the two charges further apart, the force between them is reduced, or in other words, the effect of one charge on the other becomes less. Now this is expressed as an electric field, and we define the electric field as a region surrounding a charge where its effect can be felt by other charges. But can we measure electric field? Can we tell whether a field is strong or weak? Of course we can, and we express the strength of an electric field by its electric field intensity, which is defined as the force on a unit positive charge placed at a point in an electric field. Let's try to find it mathematically. We have two charges of magnitude q and q dash placed at a distance r from each other. We will try to find the electric field intensity because of q at a distance r from it. According to Coulomb's law, the force between q and q dash is given by 1 over 4 pi epsilon naught q into q dash over r square. Now we defined electric field intensity as the force on a unit charge. So if I divide F by q dash, I get a force per unit charge given by 1 over 4 pi epsilon naught q over r square. So I have an expression for electric field intensity. E is equal to 1 over 4 pi epsilon naught q over r square. Now electric field intensity is a vector quantity, therefore it must have a direction. So I introduce a unit vector r to show its direction. Now this unit vector r would be directed away from q if q is a positive charge, and it would be directed towards q if q is a negative charge. We've just seen what do we mean by an electric field. We've seen what its strength is at different points, but how can we visualize an electric field? How can we look at an electric field? Now we can depict an electric field on a paper using electric field lines. Remember, we defined electric field intensity as the force on a unit positive charge. So at a point in an electric field, the direction of the electric field is the path taken by a positive charge. On the screen you can now see the electric field pattern because of a positive charge. Remember, the electric field would be directed away from a positive charge because a test positive charge would be repelled by this positive charge. For a negatively charged object, the field lines are directed towards the charge because a negative charge would attract a positive charge, and therefore the field is directed in towards the negative charge. Behind me you can see the field between a positive charge and a negative charge. A test positive charge would be repelled by the positive charge and it would be attracted by the negative charge. Therefore the field lines start at the positive charge and go down to the negative charge. This is the field between two positively charged particles. Now you can see that the lines are too close together and they would tend to repel each other. Also note that there is a point marked X where the resultant flux intensity is 0, and this point is called the neutral point. These are the patterns between two parallel plates. The first one is for two parallel plates which are infinite, and the other is for two parallel plates which are of finite length. Now let us try to understand a new concept called electric flux. We will try to understand this with the help of a little demonstration. Now here I have this sheet, and I say that this is a sheet which carries positive charge, and the field would be directed outwards, and the electric field is represented by these nails. These nails are uniformly spaced from each other, so therefore this represents a uniform electric field. Now if I lower this loop down onto these pins, then the number of pins that are enclosed in this loop will depend on three things. First of all, it will depend on the density of the pins. This plate contains less number of pins per unit area, and this plate contains a higher number of pins per unit area. So when I lower this loop onto this plate, it encloses less pins, but when I lower it onto this plate, it encloses a bigger number of pins. Now the second thing on which the pins enclosed depends is the diameter and the area of the loop. This loop is a bigger loop, therefore it encloses more pins. This is a smaller loop, therefore it encloses smaller number of pins. Thirdly, it depends on how I lower this loop. When this loop is lowered parallel to the plate, it encloses maximum number of pins, and if I lower it at an angle, then the number of pins included becomes less. And if the loop is lowered perpendicular to the sheet, then it does not include any pin at all. Now we will describe another quantity called area vector. This loop encloses an area, and the area vector associated with this loop has a magnitude equal to the area of this loop and has a direction perpendicular to this area represented by this pin. Now we define electric flux as the dot product between electric field intensity and the area vector. Now this pin represents electric field intensity and this pin represents the area vector. When the area is lowered horizontally, then the angle between electric field intensity and area vector is 0. When it is lowered at an angle, then you can see what is the angle between the area vector and electric field intensity. When it is lowered perpendicularly down, then the angle between the electric field intensity and the area vector becomes 90. The electric flux is defined as the dot product of electric field intensity and the area vector, and it is represented by the Greek symbol phi. So phi E is equal to E dot A, which is equal to EA cos theta. Now when theta is equal to 0, cos theta is equal to 1 and flux is equal to EA, we get maximum flux for theta equal to 0. When theta is equal to 90, cos theta is equal to 0 and the electric flux is then also 0. If we have an irregularly shaped surface, then we can divide this surface into small patches and consider that the electric field intensity for this patch is uniform. Then we can find the electric flux during this patch and then find the electric flux for all the different patches and then add the individual fluxes to get the total flux. Here you see this irregularly shaped surface. This has been divided into a number of patches. Here you can see two patches, delta A1 and delta A2. The electric field intensity through delta A1 is E1, and therefore the electric flux for this patch delta phi 1 is equal to E1 dot delta A1. Similarly, the flux for the second patch is delta phi 2, which is equal to E2 dot delta A2. Now when I add the individual fluxes, I get the total flux phi E equal to sigma E dot delta A. Let's try to find out the electric flux at the surface of a closed object because of a charge placed at its center. This ball represents a spherical closed surface. Let's assume that we have a charge placed at its center. Now all the points on the surface of this ball are at an equal distance from the center. Therefore, the electric field intensity at all the points is equal. Now if this red pin represents the electric field intensity and the other pin represents the area vector, then for a small patch on this ball, the area vector and electric field intensity are both parallel to each other and the angle between them is 0. Now here we have this ball and a small patch shown on it. The area of this patch is delta A1 and the electric field intensity through this patch is E. E is equal to 1 over 4 pi epsilon naught q over r square. Now the electric flux through this patch is equal to E dot delta A1, which is equal to E delta A1 cos of 0. Cos 0 is equal to 1, therefore this is equal to E delta A1. Now similarly, the flux through another patch of area delta A2 would be E delta A2. If I can divide this ball into n number of patches, then the total flux would be phi E equal to delta phi E1 plus delta phi E2 plus so on up to delta phi E n. This can be written as E summation I equal to 1 to n delta A n. Now this represents the total surface area of the sphere, which is equal to 4 pi r square. Now multiplying this with the electric field intensity, I get phi E equal to q over epsilon naught. Now this result tells me two very important things. The flux only depends upon the charge present inside the body and it depends on the medium present inside the surface. It does not depend upon the shape of the object.
Dear students, you have just studied that the total flux passing through any closed surface due to a charge q is equal to q over epsilon naught. Now we come to a very important law in electrostatic, which is known as Gausses law. Look here. We have a closed surface S containing charges q1, q2, q3 up to qn. We have to find out the total flux passing through this closed surface due to all these point charges. If phi is the total flux, then it will be equal to phi 1 plus phi 2 plus phi 3 up to phi n. Now what is the flux passing through this closed surface due to charge q1? Yes, you have just studied. It will be q1 over epsilon naught. Similarly, phi 2 will be equal to q2 over epsilon naught. Putting all these values in this equation, we have phi is equal to q1 over epsilon naught plus q2 over epsilon naught plus q3 over epsilon naught up to qn over epsilon naught. Taking epsilon naught as LCM, we have q1 plus q2 plus q3 up to qn. Now the quantity in numerator actually represents the total charge enclosed by the surface. So we denote it by q. Therefore, phi is equal to Q over epsilon naught. We can write this equation as phi is equal to 1 over epsilon naught multiplied by Q. This is the equation of Gauss's law, which states that total flux passing through any closed surface is equal to 1 over epsilon naught times the total charge enclosed by the surface. Now we are going to discuss some of the applications of Gauss's law. Look at a situation here. We have a sheet of infinite extent on which positive charge is uniformly distributed. We have a point P here, and we have to find out the electric intensity at this point P due to this infinite sheet of charge. We will apply Gauss's law to solve this problem. Before going into mathematical detail, we will imagine a cylindrical surface like this. It has three surfaces, one end face, second end face, and the curved surface. Look here in the figure. We have the cylindrical surface which is passing through the infinite sheet of charge. Now, Gauss's law demands that we must know the total flux as well as the total charge enclosed by the surface. Now, the total flux will be due to this end face, and the curved surface. If we denote the total flux by phi, then phi is equal to phi 1 plus phi 2 plus phi 3. What is phi 1 here? Yes, it is the flux passing through one end phase. So phi 1 is equal to E1 dot A. By the definition of dot product, you know that E dot A is equal to EA cos theta. Now what do you think about the theta here? Look at this one end phase. Here we have an area. The direction of area is always normal to the surface. So this is the direction of the area. The direction of electric field is also this. So what do you think about the angle theta? Yes, it will be 0. Therefore, phi 1 is equal to EA cos of 0. Now cos of 0 is equal to 1, so phi 1 is equal to EA. If phi 2 is the flux passing through the other end phase, then by the same treatment we will have phi 2 is equal to EA. Now what about phi 3? This is our curved surface. This is the direction of any small area taken on the curved surface. So the direction of A is this. The direction of E is this. What is the angle between them? 90 degree. So phi 3 is equal to E dot A, EA cos theta. Here theta is equal to 90 degree. So phi 3 is equal to EA cos of 90, and cos of 90 is equal to 0. Therefore, phi 3 is equal to 0. Yes. Putting the values of phi 1, phi 2 and phi 3 in equation 1, we have phi E is equal to EA plus 0. Phi E is equal to EA plus EA, yes, 2EA. Now we have to find out the charge enclosed by the cylindrical surface. If sigma is equal to charge density, that is charge per unit area, then charge Q is equal to sigma into A. This is our equation number 3. Now the equation of Gauss's law is phi E is equal to 1 over epsilon naught multiplied by Q, the total charge enclosed by the surface. We have the value of phi E from equation 2, put it here. We have the value of Q from equation 3, put it here. We have 2EA is equal to 1 over epsilon naught sigma A. From here, the value of E is sigma A over 2A epsilon naught. A is cancelled with A, and we are left with E is equal to sigma over 2 epsilon naught, And if you want to write down this in vector form, we have E vector is equal to sigma over 2 epsilon naught into R unit vector. Now we come to the second application of Gauss's law. Here we have another situation. Just see the figure. Here we have two oppositely charged parallel plates of infinite extent, and we have a point P in between these two plates. We have to find out the net electric intensity at point P due to these two plates. For this, look at the situation. We have a point P and a sheet of infinite extent. So the result you have just studied can be applied here, and the value of electric intensity at this point P due to this positively charged sheet will be sigma over 2 epsilon naught. But what about the direction of electric intensity? If you want to find out the direction of electric intensity, put a unit positive charge here at point P and see in which direction this unit positive charge will move. Obviously, it will move from positive plate to negative plate. So the direction of electric intensity due to this plate, which is denoted by E1, will be from positive plate to negative plate. Now we find the electric intensity at this point P due to this plate. Again we have the same situation. We have a point P and a sheet of infinite extent. The result is the same. Electric intensity is sigma over 2 epsilon naught. But what about the direction? If you put a unit positive charge here and see in which direction the positive charge move due to this plate, obviously it will move in this direction. So the direction of electric intensity E2 will also be from positive to negative. In other words, the net electric intensity at this point P will be equal to the sum of electric intensity due to this plate and also due to this plate. Therefore, E is equal to E1 plus E2. E is equal to, the value of E1 is, yes, sigma over 2 epsilon naught. What is the value of E2? Sigma over 2 epsilon naught. Taking the LCM, we get E is equal to 2 sigma over 2 epsilon naught. This 2 is cancelled with this 2, and we are left with E is equal to sigma over epsilon naught. In vector form you can write down this equation as E is equal to sigma over epsilon naught into R unit vector. Just put a vector here. Dear students, now we come to another important idea in electrostatic, electric potential. Look here at this object. If I want to move this object from this point to this point, I have to do work on it. The work I have done on this object in lifting it from this point, that is from point of lower potential to a point of higher potential, that work will be stored in the body in the form of its gravitational potential energy. We have a similar situation in electric field. Look here. We have a plate A which is positively charged, another plate B which is negatively charged. If we want to move this charge Q naught from plate B to plate A against the direction of electric intensity, we have to do work on it. This work will be stored in the charge in the form of its electrostatic potential energy. But if we want to move a unit positive charge from point B to point A against the direction of electric intensity, then again the work done will be stored in the charge in the form of its potential energy, but this potential energy is known as potential difference between the 2 points. We have a charge Q naught here. We want to move this charge Q naught from plate B to plate A, keeping it in electrostatic equilibrium. The work we will do to bring this charge Q naught from plate B to plate A will be stored in the charge Q naught as its electrostatic potential energy. On the other hand, the work done in moving a unit positive charge from one point to another point against the direction of electric intensity, keeping it in electrostatic equilibrium, is known as potential difference between the 2 points. Dear students, you might have listened about the capacitors. Today we are going to discuss a parallel plate capacitor. Look at the figure. Here we have two plates A and B. This plate A is connected to positive terminal of the battery and the plate B is connected to the negative terminal of the battery. Now positive terminal of the battery will draw electron from plate A. Due to deficiency of electron, we will have positive charge over here. These electrons are given by a negative terminal of the battery to the plate B. So we will have equivalent amount of positive and negative charge on the inner surface of these two plates. This arrangement is known as parallel plate capacitor. Now we have to discuss that what is the effect of dielectric on the applied electric field. Dielectrics are the mediums which we place between two parallel plates. This plate has positive Q charge and this one has got minus Q charge. If you place some dielectric medium between these two plates, we see that a negative charge will appear on the upper surface of this dielectric here and plus Q charge will appear on the lower surface of this dielectric. Now we have an applied external electric field in this direction, but within the dielectric we have another electric field which is opposite to the applied electric field, which is in this direction. Obviously, the electric field produced within the dielectric is less than the applied electric field, but overall effect will be that the applied electric field will be reduced due to the presence of this dielectric medium. Dielectric mediums are of two types: polar dielectric mediums and non-polar dielectric mediums. Here we have a negatively charged plate and a positively charged plate, and we have placed a polar dielectric medium between these two plates. The polar molecules will arrange themselves as you are looking here. We have a negative charge here. The positive end of the molecules will come near to the negative end. Here we have positive plate. The negative end of the molecules will come near to the positive plate. All the inner charges are cancelled out, but we will have a net positive charge here and a net negative charge over here. The applied electric field is in this direction. The electric field produced within the dielectric will be in opposite direction. And it is because of this reason that the applied external electric field is reduced due to the presence of polar dielectric medium. In case of non-polar dielectric medium, if we apply some external field over the non-polar dielectric medium like noble gases, then due to the presence of applied electric field, there will be a shifting of charges towards the end of a molecule or simply an atom. We will have a partial negative charge on one end and partial positive charge on the other end. So again, the applied electric field will be reduced by the internal opposite electric field.
Well students, this brings us to the end of this program. Do you remember what are the things we have studied today? Yes, we have studied Coulomb's law, we have studied electric field and its intensity, electric flux, Gauss's law and its applications, and we've studied electric potential and then applied all of this and studied capacitors. And in the end, we studied something about electric polarization. Well, thank you for enjoying the program and I hope that you've learned some things new today. Khuda Hafiz.